So, I've been wanting to redo my old WebGL tutorial series for a few years, and now I finally have the time to do it. WebGL is a real-time graphics API for the web, and it lets you power some really neat 2D and 3D experiences. I've seen it used in games, musician websites, and some really beautiful graphics demos. I've also seen it used for business applications. I started my professional career working on WebGL rendering code for Lucidchart, and I loved it. It's a powerful API that gives you pretty direct access to GPU processing power, but with the portability and user-friendly distribution model of the web. As much as I'd love to dive right into things, I do first want to talk about learning WebGL compared to OpenGL, and compared to the more modern WebGPU API, which I'm hoping to cover in a later tutorial series. First, WebGL is an excellent place to learn computer graphics. I can't think of a better API to start with, though of course there's no one-size-fits-all for learning. WebGL is nearly identical to its parent API OpenGL, and the important concepts are all shared with the other major APIs of its generation. OpenGL and Friends were the de facto powerhouse standards for a long time and are still really relevant today. But as your first graphics API, WebGL is nice because the browser takes care of some of the annoying overhead. In particular, your browser already knows how to process image files and how to set up a drawing surface, both of which are surprisingly hairy problems in traditional C and C++ graphics programming. It'll also help you understand the shape and behavior of higher level rendering libraries if you decide you don't want to deal with the raw, low-level nonsense yourself. Second thing, WebGL is a low-level API, but it fits into this kinda weird space for web graphics. If you value ease of use, there's awesome graphics libraries that abstract away a lot of the pain of WebGL without taking away much of the power. Three.js and Babylon.js come to mind for 3D, and Pixie.js for 2D. On the other end, if you value low-level control, WebGPU is much more developer-friendly and feature-rich. WebGL is still an amazing place to start and learn, but for most jobs there's a better tool. Don't get me wrong, WebGL can do all the things perfectly well, but before diving too far into the weeds, you should be aware that you might reach for other tools down the road. Finally, if you're not an expert web programmer, don't worry. There's actually not much web dev specific nonsense in this series, and I'll be careful to explain all the HTML and JavaScript specific features that I use. As long as you're familiar with basic programming, what with like variables, functions, and classes and whatnot, the code should look pretty familiar. And there's a Google Doc in the description that'll have links to articles, corrections to mistakes, and answers to questions from the comments in there. Check it out if you're lost. Also, please feel free to ask questions in the comments. I can promise you that if you have a question, someone else watching this later will have that same question. Still here? Awesome! Welcome to the series. The most basic thing that you can draw with WebGL is a triangle. Almost everything is triangles with WebGL, so for this video, let's draw a triangle. The name of the channel is Indigo Code, so I think indigo is a good color for the triangle itself, and let's be nice to the people who are watching this in a dark room late at night and go for a dark background. I've put this code on GitHub, link in the description, and this is the output we'll have at the end of the video in the browser on the right. As you can see, it's a lot of code. There's two pretty big reasons that even just this hello triangle program is so long, and both of them have to do with how WebGL is designed to do a lot of things very, very fast. The first is that GPUs want to do as much as they can in parallel. GPUs don't do any individual task very quickly, but they can do a lot of tasks at the same time. Splitting up drawing work into parallelizable chunks takes some doing. The second is that GPU has its own memory regions that work pretty differently from the main memory you're used to working with as a programmer. Sending that data over to the GPU in a way that WebGL can work with takes quite a bit of setup work. Let's do a quick conceptual run-through of what our app is going to have to do to draw this triangle. First, unsurprisingly, we have to come up with a definition for our triangle in JavaScript application logic. We define our triangle as 3 points. For this video, we just need an X and a Y coordinate for each, but you can attach whatever properties you'd like. In future videos, I'll talk about adding more properties that are useful for 3D and certain graphics effects. But this is a JavaScript array, and it exists in main RAM. We send the raw data to the GPU as a GPU buffer, a buffer just being a chunk of bytes. We use 3 corners, or vertices, consisting of 2 numbers each, and those numbers will be 4-byte floats for this video, so a total of 24 bytes of GPU buffer data is used. We also have to specify how the GPU is supposed to read data out of that buffer by declaring attributes for our buffer. In our case, we have one attribute, position, which is a pair of 2 numbers, each one being a 32-bit float. The next step is the vertex shader, which is the first place where GPU parallelism comes in really handy. Each vertex gets run through a little program we write in order to decide where that point should go. The output is in clip space, where x goes from -1 on the left to 1 on the right, y goes from -1 on the bottom to 1 on the top. There's also a z and w value, which I'll talk about in a later video about drawing 3D objects. Once all the vertices are processed, the next step is primitive assembly, where the GPU figures out what corners go to which triangles. Us application developers don't do much here, we just tell WebGL to use triangles. By default, WebGL just organizes vertices in groups of 3, but you can do fancier things if you'd like. The next stage is rasterization, where the GPU looks at the dimensions we told it to render to, and comes up with a list of pixels that should be drawn to the output, called pixel fragments. This part right here is why triangles are so useful for graphics APIs. Rasterization is really simple for triangles compared to other shapes. The graphic in this video uses a 50 by 50 image to really highlight what rasterization looks like. Now we have this huge list of pixels that needs to be drawn, and we get to another place where GPU parallelism comes in really handy. Each one of these pixel fragments produced by the rasterizer goes through the fragment shader, which is another GPU program that you write. This one outputs the color that the given pixel should be as an RGB color. For this demo, we tell it to draw every pixel indigo, which is 29.4% red, 0% green, and 51% blue. You can do some really fancy things here. Fragment shaders themselves deserve an entire tutorial series on their own. Finally, the last stage is blending or output merging, where WebGL takes the output image, looks at what colors are already on that image, and decides how to combine the fragment shader output and the existing image together. We aren't doing anything fancy here. Overwrite the background color with the triangle color, and that's it. Alright, so enough with the theory, let's get to the actual code, yeah? So I have right here an index.html file. This is where we're going to tell the browser what things we want to actually show up on our web page. And then I've made a hello triangle JavaScript file in the same directory where we'll actually be writing our JavaScript code. So the first thing I'm going to do is I'm just going to copy and paste from my notes, the index.html. You can see there's a whole bunch of stuff here. For us, the only thing that actually is going to matter is the little thing in here inside the body tag. I have this canvas element. This is an element that sets aside a little area of space on the page that we can draw to using the WebGL API. I've also put in for myself this little error box thing right here. It makes it a lot easier for me as I'm recording. If there happens to be an error, I can see it on the screen that I'm actually looking at. And when you're looking on mobile, you don't have access to the developer console, so the only way to see errors is if you put them on the page itself. And the last thing is the actual script element right here. This tells the browser to load the JavaScript at this file after it's already processed that the canvas and the error section are already there. Everything up here is going to be mostly just this styling. I have a little bit of metadata that kind of comes default with HTML pages that you write. What I've done here is added some white space so that it looks just a little bit more pretty. And then I've also set the background color to this dark gray so that I don't burn the eyeballs out of anybody who's watching this on a bright screen late at night. And then for the canvas itself, I've set it to have 800 pixels wide and 800 pixels tall, just a nice square shape, pretty big. You can make this whatever you want. And then the last thing I've done is a little trick that I learned from WebGLfundamentals.com, where I've given the default background color of our canvas this salmon color that I know isn't going to show up anywhere in the demo, so that if you see that color appear on the canvas, you know that you messed up the transparency somehow. So moving on to the JavaScript file, let's get to work. The first thing that I'm going to write is just a little bit of code that's going to help me handle errors. Alright, so what I've done is I've just written this show error function that finds that error box section that we put on the page, creates a new paragraph element. This is an HTML element that just takes some text, sets the text on that element, and adds it to our box area. And if I load our page over here, you can see this is what our page looks like so far. The error that I printed out shows up, fantastic, and we have this canvas area that's that, again, just bright salmon color that we know isn't right. So let's get into the actual tutorial code now. All right, so I've decided that I want to put the entire demo functionality into this hello triangle function, and then I'm going to, as soon as it's done being defined, immediately try to execute it and catch any unhandled exceptions. In the case that I have a dumb typo or something, I want that error to appear. Inside the hello triangle function, the first thing we need to do is to get a reference to the HTML canvas element that we made earlier. Once we have that, we can use it to get a WebGL rendering context, the object used to interact with the WebGL API. So I've done a few things here. You can see I get a reference to the canvas the same way as I did up here by using this document.getElementById. This line right here is actually a comment that's completely ignored by the browser. You don't need it at all in your JavaScript code. I've included it for the IDE because this gives a little hint to Visual Studio Code that, hey, this element is a canvas element, not just a generic HTML element. I then check to make sure that we actually got a proper reference. If it failed, it's probably because you have a typo somewhere or because you loaded the script too early in the HTML. And then I go here and I get the WebGL 2 rendering context. There are technically two versions of the WebGL API, but WebGL 2 has been out long enough that you should really just be using the more recent one. If this GL object comes out empty, we need to show an error that this browser doesn't actually support WebGL 2 and stop the demo. For my version that I'm going to be posting to my website, I am going to check for WebGL 1 support just in case I have a visitor who's in one of those weird corner cases where WebGL 1 is supported but not 2. Fantastic, we now have a WebGL context. I do want to point out that canvas and GL are not special keywords. Naming the context GL is a convention that a lot of WebGL programmers do. 2 letters is very easy to type and you do type those letters a lot, but at the end of the day, it is just a variable name for the context object. So the first thing that we need to do in our WebGL demo is we need to actually clear the canvas. You can see right now that it is just this plain background, and that is because the image that WebGL is going to render to is just a transparent image on top of this canvas element. We want to replace that transparent image with a dark gray one that we're going to use for our background. Now the gl.clear command that I'm using right here is the first place where WebGL starts to get a little bit weird. WebGL doesn't just have one image that it uses that you're drawing to, it actually has 3 buffers. The first one is the image, the actual picture that has all the colors that you're drawing things onto. The second one is called the depth buffer, and that stores depth information for each pixel on the output image. And then the final one is the stencil buffer, which is used for certain graphics effects that I won't be covering. Now for us, we're going to need to clear both the color buffer and the depth buffer, so I will do that like so. Great! These 2 lines clear both the color and depth buffers. Now, WebGL picks up a couple C-style programming things from OpenGL, which is an API for the C programming language. One of them is the use of bit flag parameters, which is an old school way of sending in multiple booleans to a function by setting individual bits on a single integer instead of sending in a bunch of parameters. Both color buffer bit and depth buffer bit are integers with a single bit set to 1, the other set to 0, and you can combine them together with the bitwise OR operator like this. And now with one call, WebGL will clear both the color and depth buffers. Going back over here, we can see if I refresh, nothing changed, it's still transparent. The reason for this is that by default, the clear is actually still just a transparent image, so we need to tell WebGL what color we want to clear our canvas to be. And you do that using the WebGL clear color method. And this takes 4 parameters, the red, green, and blue value as fractions between 0 and 1, or ratios between 0 and 1, and then an alpha number, which stands for the opacity. Opacity being the inverse of transparency. So 0 means completely transparent, and 1 means not at all transparent. If I come back over and I refresh our page, you can see now we're clearing to this much darker gray background. All right, fantastic. So now let's get to drawing the actual triangle. So the first step is that we need to define the data that the GPU is going to use. And if you remember from the theory section of this video, we need the actual vertices for the triangle, vertex being a corner of a triangle, and then we need the definitions for our vertex shader and our fragment shader. So let's start out with the actual triangle definition. I'm going to make a JavaScript array that has the X and Y positions of each of the corners. Cool, as a reminder, these values are in clip space. We have x equals 0 right in the middle of the viewport from left to right, and y equals 1/2 is 3/4 of the way to the top of the viewport. Remember, y equals -1 is at the bottom, and y equals 1 is at the top of the screen. This coordinate in the bottom left has values -0.5, which is 1/4 of the way both left to right and bottom to top, and the bottom right coordinate is similarly formed. Now, for decimal numbers like this that have a fractional component, GPUs really like to use a 32-bit float, where JavaScript is using 64-bit floats. JavaScript arrays also don't necessarily have the guarantee that all of these numbers are next to each other in memory, and we do want just one chunk of data that represents the vertices of our triangle. So in order to put our triangle data into a format that the GPU is going to like, we put it into a float 32 array. All right, and I've put that into a new variable, this triangle vertices CPU buffer. This is just to indicate that this is a CPU visible buffer that contains the actual data that we need to send to the GPU. Now, we need to actually send this data over to the GPU. The GPU can't read JavaScript variables. So to do that, the first thing that we do is we create a buffer on the GPU using the gl create buffer command. And this command creates a WebGL buffer type. And you can see it's possible for this to be null. I'm not actually going to check for null in this program. It's a good idea in a production application to do that. You'll run into that if you can't actually create any new buffers. Now, this WebGL buffer type is what we call an opaque handle. So when you talk with the WebGL API about a WebGL buffer, it knows what you're talking about, even though the variable itself doesn't have the data. All right, and so this right here doesn't actually create the memory yet. It's a little bit more complicated. We have to first attach this buffer to what's called a WebGL attachment point. And the one that we want to use is called the array buffer attachment point. This is what's used for vertex information. All right, so now this buffer handle is attached to the array buffer attachment point. We can use a buffer data command to say the thing that's bound to this array buffer attachment point, give it this data. All right, so this is kind of a weird layer of indirection where we have to first put it in the array buffer slot and then we can communicate with WebGL what data to put there. And then we also have this next parameter right here, static draw, which is a hint to WebGL on how we're going to use that data. And the reason for this, when you make a variable normally in CPU side programming, there's only one place that it's going to go. That's to your main RAM. That's where memory lives. But on the GPU, you have a whole bunch of different places that that memory can go, and they have different characteristics. And different GPUs are going to have different types of memory available. So this gives WebGL a hint so that your graphics driver can kind of pick where it should put the memory. By specifying array buffer, we indicate that this will be used for vertex data. And then this gl.staticDraw, we're telling WebGL that we don't intend to update this data very often, but we might be using it very often. The most important thing that this call does, though, is it says whatever thing is bound here, this triangle geobuffer in this case, we need to give it a chunk of memory on the GPU that is big enough to hold the data in this CPU side buffer, and we need to send this data over to the GPU. So at this point, we now have data in this triangle geobuffer, and it contains all the ones and zeros that form this array right here. Fantastic. So our buffer is set up and it's sent over to the GPU. Now we need to set up our vertex shader and our fragment shader. Those are going to be written in a programming language called glsl, which is very efficient and optimized for running programs on the GPU. Unfortunately, we have to put that source code inside of our little JavaScript program here and then send it over to the GPU and compile it for use on the GPU all in here. Great, so the first two lines of any vertex shader in WebGL are going to be this pound version 300 ES with no semicolon. And this has to be on the very first line, mind you can't have a new line before it. And this tells WebGL which version of the OpenGL shading language we want to use. In this case, it's version 3.0 mobile standard is what ES means. The next line, precision medium p float, is kind of a fun one. GPUs can do some really weird stuff with how they do floating point arithmetic, and this tells it how precise we need it to be. Medium p is a really good default. In almost all cases, medium precision and high precision are going to look the same, so you might as well just use the fast or medium precision. And especially on mobile devices, high precision can run really slow and use a lot of battery life. So this is just a good default, especially if you're supporting mobile. The entry point of a vertex shader is this void main function. The way that inputs and outputs are handled are kind of weird in GLSL. It takes inputs in what is called an attribute, which is expressed like this. We use this in keyword to specify this is an attribute that we're going to be getting from some buffer that we've specified, this data right here. Vec2 specifies that it's going to have two floating point numbers in it. WebGL uses a lot of linear algebra. It's a branch of math very useful for graphics programming, where these vectors or groups of 2, 3, or 4 numbers comes in really handy. This one tells us that it's a two-dimensional. It has an x and a y, and that they're both floats. And then finally, we give it a name. This is just a variable name that we can use. So the job of the vertex shader is to declare where the vertex that is going through and being processed right now should show up on the output image in clip space in that -1 to 1 x and y dimensions. Now we've already defined our x, y, and z in those dimensions, so we can just output the same number. That output variable has the special name gl_position. Every vertex shader has to set this variable somewhere, and glPosition has a type of vec4. It's a 4-dimensional number, so kind of weird thing. The first two we get from the x and y of our vertex position. You could also write that out in a long form like this. Could do this if you wanted to, but WebGL does know that if you put a vec2 as the first parameter to just expand it like this. So I'll just do it the short way. This third number right here is z, or the depth information, and this has to be a number between -1 and 1. This has to deal with how does WebGL draw things that are overlapping with each other. If you have 2 pixels that are trying to go to the same spot in the output, which one shows up on top of the other? That's determined by this third value right here. Anything between -1 and 1 is fine. I just pick 0. This fourth number is a special one, w, but for now all you need to know is the number here. The x, y, and z values will get divided by this fourth w value before they actually get processed by the next stages. So I want to set 1.0 here because any number divided by 1 is just that same number. Great, so now this is the entire source code for our vertex shader that we want to run. Now, similarly, we have to send it over to the GPU. And we can do that by creating a shader, setting the source code, and compiling it, kind of like how we created a buffer, bound it, and then sent over the data up here. Fantastic. So now we have our shader that we've created. We've told WebGL that it is a vertex shader. We've set the source code on it, and we've told WebGL to compile it. One thing that you're going to run into all the time is it is so easy. You can see that this is all just a string. I don't have any sort of syntax completion. I don't have any IDE tools to hold my hand and make sure, the Indigo code doesn't make a mistake anywhere. I can have all sorts of typos and problems in here. It's a really good idea to check to make sure that there weren't any compilation problems. And you can do that like this. Let me scroll up a little bit, so that's in the middle of the screen. So this is a little bit of a weird holdout, again, from the fact that WebGL comes from a C API OpenGL. Things are structured in this weird way. We check this getShader parameter on the vertex shader. The parameter that we're checking is compile status. It's another one of those funky numeric constants that C-style APIs love so much. And if this returns false, it means that there was a problem. We can get a text string of what that problem was by doing this getShader info log to give us the compile error and display that error on the screen if something happened. I'm also going to return because if there is a problem compiling, we won't be able to finish the demo. All right, and let's just make sure everything is fine. I'm going to pull this up and refresh. Everything was. But if I introduce a typo here, let's say, whoops, I misspelled that variable pretty bad, didn't I? I can refresh this and I can see vertex error failed to compile because this variable was undefined. Super helpful. You should always do that. Seriously, I run into so many compile errors even though I've been doing this for a long, long time now. Great, so now the vertex shader is declared and has been sent over to the GPU. Let's do the same thing for the fragment shader. Now the fragment shader has the same boilerplate, this version 3.0 ES, use precision medium p float, void main, and this time we're going to be outputting the color, and in our case we want to use the color indigo specifically. Unlike the vertex shader, which has a built-in glPosition variable, we have to specify output variables manually with a fragment shader. This is because vertex shader outputs always have to have at least a vec4 clip space position output, but fragment shaders don't have any required outputs like that. You can have a single RGBA color output like we want here, but you can also have a single channel depth output for shadow map generation, or maybe multiple RGBA color outputs for HDR or deferred rendering outputs, something like that. WebGL will attach our single RGBA color output to the color buffer by default, so name it whatever you want. The output color is also a vec4, so we output it like so, and I just say 29.4% red, 0% green, 51% blue, that is the color indigo, and 1.0 for this is a not at all transparent, fully opaque pixel that we want to draw. So just like how we compiled our vertex shader, we also need to compile the fragment shader. I'm just going to copy paste this. It is basically the same. Fantastic. You can see it's basically the same thing, except for this time we need to tell WebGL we're using a fragment shader instead, but all the other commands are the same. Now, an interesting thing with WebGL is you never actually use a vertex shader or a fragment shader independently. You always combine them and use in a combined object called a WebGL program. Great, so what I've done is I've created this WebGL program and I have attached both our vertex shader and our fragment shader to this program. The next thing I need to do is I need to link the program, and that is to make sure that the vertex shader and the fragment shader are actually compatible with each other. And just like how we checked for compile errors earlier with our shaders, we can also check for link errors to find any incompatibilities between our vertex and fragment shader. You can see the error checking commands here are the same as they were before, except for using the word program instead of shader and link instead of compile. Pulling our window back open, let's refresh and make sure that everything works well. Fantastic. Awesome. The next thing that we need to do, now that we have our vertex shader and fragment shader combined together into a program that WebGL can actually use on the GPU, we need to get a handle to this vertex shader input so that we can tell WebGL how to read this data later. The way that we do this is we get what's called the attribute location of this input. The attribute location is just going to be an index. Which number of attribute is it? For this one, there's only one, and attribute locations start at 0, so we know it's going to be 0. If I were to put in more, they would go 0, 1, 2, etc. It's still generally a good idea to ask through WebGL what the location of each attribute you're interested in is, because it's so easy to accidentally reorder them or for one of them to be optimized away without you realizing. So let's still ask. Great, so this will get the attribute location of this vertex position attribute in our vertex shader and put it into this variable right here. And you and I both know this variable is just always going to be 0, but this is educational content, so let's do it the right way anyways. And I'm going to check to make sure that we actually got the correct attribute location. You can do that by making sure that this variable is at least 0. It will be -1 if this call fails. Let's pull up our demo window. Fantastic, it looks good. If I introduce a typo, then blammo, we get our error. Awesome. So if you were writing a program that was actually presenting a lot of these images very fast for like a tool or an animation or a video game or something, all of this stuff you would usually do in like a loading screen, because this all just needs to be done ahead of time, getting the information over onto the GPU. Once shaders and geometry are on the GPU, they can be used very efficiently in drawing commands. We first need to configure the graphics pipeline, and once it's configured with the state, shaders, and geometry that we want to use, tell WebGL to draw the triangle. The pipeline stages that need to be configured are the ones that I talked about in the beginning of this video. I'll write a quick comment for each and then go through how to set them up one by one. Great! 6 comments, one for each of the 6 steps I covered earlier. The first one I want to talk about is primitive assembly. Of the pipeline stages, this is the one that requires the least input out of the application developer. We just need to specify how triangle vertices are grouped as part of the draw call, so let's move this to the bottom. The order of the remaining 5 doesn't affect the final image at all. No rendering work is done until the draw call, so you can pick any order you'd like, as long as all 5 of these are configured when the draw call is made. That said, there are performance considerations. As a rule of thumb, changing state takes time. When there are a lot of things to draw, you'll usually have objects that share state. Lots of trees that all need tree shaders, a handful of humans that all need the human shader, all being drawn to the same output texture and viewport. It's worth taking some time to think about how to batch together your calls to avoid switching state back and forth if you can. I'm going to go with a generally good ordering that I use a lot, but of course for this app it's totally unimportant because everything is configured once for drawing one object. First up is the output merger. Everything will be drawn to the final output image, which is set once per frame. Second is the rasterizer, configured to draw to the whole output texture. Some apps might update this a couple times per frame, for example to draw a bitmap to the corner of the screen and then the rest of the scene to the whole screen. Next is the vertex and fragment shader, which if you remember from earlier are set in a single object together as a WebGL program. Programs are swapped out for each graphics effect, but generally speaking there will be quite a bit of geometry with relatively few shaders. Finally is the input assembler stage, which will generally change for each piece of geometry that you draw, updating input attributes to pull from the vertex information for each unique thing. So to set up the output merger in WebGL, this is actually pretty easy. We just need to make sure that the width and height properties on our canvas element are the size of the image that we want to draw to. What I'm doing here is I am setting the width and height property of the canvas to the actual HTML pixel size that it is going to take up on the screen. And these don't necessarily have to match. You can set the width and height to different numbers, and this creates an image that will be stretched or shrunk accordingly to put into the correct area. Now, as just a weird little thing, I'm going to come over here once I've done this and I'm going to refresh the page, and you'll see that it's gone back to this salmon color. Whenever you set the width or height of something in WebGL, it generates a new image that is going to have the wrong color. It's going to be that default transparent color again. So I need to move that clear code to underneath this width and height adjustment. Great, that's looking better. Cool, so now our output image has been configured. Next, we need to set up the rasterizer. It is possible for you to run the pipeline on only a part of the screen. Let's say that you have a mini map that's up in the upper right-hand corner of the screen. You don't want the rasterizer to have to waste its time thinking about the rest of the screen, so you can tell it, hey, just focus on that upper right-hand corner. And the way that you specify which part of the screen should be used is the GL viewport command. And the 4 parameters for this command are the X and Y coordinates on the image to start at, and then the width in pixels of the region that we want to draw to, and the height in pixels of the region that we want to draw to. Just the width and height of the canvas respectively. And that's it, rasterizer is set up. Fantastic. So the next thing that we have to do is to set up the GPU program. We have to tell WebGL which program we want to use, and this is kind of a weird thing. We have to enable each one of the attributes that we want to use. Don't know why WebGL does this, but you do have to remember to do it. Great, and so that's it. GPU program is all set up, WebGL is ready to use that program. The next step is easily the hardest step in this tutorial, and that is going to be to set up the input assembler. This is going to tell WebGL for each one of these input attributes that we have in our vertex shader, in our case it's just the one, for vertex position, which buffer are you going to read from, and then more importantly, how do you read that information into this vic2? Because once you've sent the data over to the GPU, it's in just this string of ones and zeros. The GPU doesn't know anything about what types are in there, what data is in there, if it's like integers or if it's floats or if it's bytes or what. And the way that we do that is through the vertex attrib pointer call. But the first thing that we have to do is we have to make sure that the buffer that we're pulling data from is bound to that array buffer slot. This binds that triangle GeoBuffer to the array buffer slot. And if you remember from earlier, we already did this. So this is already the buffer that's bound to the slot. It is a really, really good idea to make sure before you start doing your vertex attrib pointer calls, though, that you specify right there at the same time, hey, this is the buffer I want to use. It is just too easy to make the mistake of knowing offhand that some buffer is attached, writing your code, updating it in a totally different section of your code later and forgetting about it, and then having just really bad wonky errors down the road. All right, and this call takes 6 parameters, and I'm going to go through them one by one. The first one is index. Index is the attribute location that we got earlier. Nice and easy, vertex position attribute location. The second parameter, size, is going to be the number of components in that attribute. All right, the third one is type. And this is a little bit strange. You might think that type is like what the type of the data is. It is specifically what is the type in the GPU buffer that we're reading from of this attribute. This type doesn't necessarily have to be the same type that is in our vertex shader up here. In our vertex shader right here, it is a pair of floats. And in the buffer that we specified, it is also a pair of floats. But the one that this type call has to be is specifically what is the type in the actual buffer itself. All right, and the next parameter is normalized, which has to do with how you convert from integers into floats. It is possible to have integer data in your GPU buffer and then to convert that into floats. If you set normalized to false, it will convert those numbers just into the closest floating point number. The integer 1 becomes the float 1.0. The integer 17 becomes the float 17.0. If you set it to true, then it instead normalizes the integer range down to the floating point range -1 to 1. So let's say that you have an 8-byte signed integer, which goes from -127 to +127. The number 127 would be converted into 1.0. and the number 63, which is halfway between 0 and the maximum, would be turned into a 0.5, etc. Usually, just set this as false unless you really know what you're doing and you're doing something fancy. And in our case, where we're using floats anyways, it doesn't matter if you set it to true or false. This parameter is totally ignored. And the last two parameters, stride and offset, are a little bit tricky to think about if you're not used to pointer arithmetic, and they have to deal with the spacing in the buffer that you're dealing with. So I'm going to start with this offset parameter, which specifies how many bytes forward should the input assembler read into our buffer before it starts to read the attribute data. In our case, the very first attribute begins right at the very first byte, so don't skip any bytes, 0. Stride tells the input assembler from the first byte of an attribute for one vertex, how many bytes do you have to move forward to get to the first byte of the same attribute for the next vertex. So how far do you have to move forward in bytes to get from the first position to the second position in our buffer? There is this special number that we can use, 0, which tells WebGL, you figure it out, you know how many components are in the attribute, and you know what type they are. You just do that yourself, figure that out yourself, and that works totally fine. However, if you want to, you can also do this yourself and say, okay, it's 2 times the size of a float, and because this is educational content, I am going to leave it in this long form like that. Fantastic. So now at this point, we have our entire GPU state set up, and we just need to execute the draw call, and we do this using the GL draw arrays method. And GL arrays takes 3 parameters. The first one tells the input assembler how do you organize the triangles together. We just tell it basic list of triangles. Second parameter is what is the first vertex that we should look at. In this case, it's at index 0, start from the very first one. And the third one is how many vertices do we want to process. One triangle is made up of 3 vertices. We have one triangle showing on the screen, so 3. All right, and assuming I didn't make any horrible mistakes, yay, now it's an indigo triangle. Fantastic. And there you go. That is the hello triangle. This is the most basic WebGL program you can write. As you can see, it is 130 lines. That's a little bit nuts. I did put in a little extra stuff that doesn't really need to be here, but for the most part, this is the basics. And that's it. Take a deep breath and appreciate how much information you just took in. One of my favorite things about running this channel is seeing all the insightful comments from my viewers. As people make nice observations and find mistakes I made, I'll be posting updates to the companion page linked in the description. There's also a text version of this tutorial and a link to the tutorial source code there as well. The next tutorial, tentatively titled Motion and Color, will cover drawing many different shapes to the screen. I'll cover some of the neat things you can do with vertex attributes, passing additional parameters to shaders, and a more modern way of building input assembler data called vertex array objects. I hope you enjoyed this tutorial, and I hope you keep following along to learn more about graphics programming with WebGL. Until next time.